we start?
Yeah. Hey, welcome back for the last session of the day. Okay, so today, Sofia, you're going to talk us about quantum machine learning and high energy physics. Thanks.
Thank you. So thanks for the invitation. I'm very happy to be here. I'm learning a lot of things, although I just listened to very, very few talks, and I apologize to the other speakers for that. So I will talk to you about quantum machine learning in high energy physics, and I explicitly wrote there examples from CERN because I will use example of what we are doing. I'm choosing among the things we are doing at CERN, but they are very much representative of actually the much broader field and applications that are happening, that are being studied in many different institutes, okay? So the talk, or my talk, I can also do it. It doesn't matter, it doesn't matter. Oh, but actually. Okay. Just a second. Okay, now it works. Okay, so I will just start with a brief introduction about the context. So I will talk to you about the Quantum Technology Initiative at CERN very, very briefly, because there is a lot of public information concerning that. And then I will really go into a set of basic concepts about what it actually means to run machine learning algorithms in the quantum domain. And then I will give you some examples. But before I start, I would like to understand what is the level of expertise on machine learning here. So how many of you, it's just because I want to calibrate the jargon, okay? How many of you work daily with machine learning algorithms? Okay. It's easy to calibrate. Okay, I will try to keep this as general as possible. So maybe some of the things I will say will look too simple, but we can always have discussion later. And if you, at any moment, you don't understand what I'm saying, because I will really try to talk in a human term, but if that does not happen, just stop me and ask me to clarify. So before we go there, I will make an additional step back. You're all quantum experts here. I would like to set the stage and let you think about quantum in terms of computer science. So if you think about all the concepts that are important in quantum mechanics and quantum technologies in general, how do they reflect, what do they mean in terms of computing? So if we look, for example, we don't need to go through all of this, but of course, if you look at superposition, the first thing quantum computer scientists think about is parallelism. Now, the point is obviously that this is a theoretical parallelism, because you can, in principle, store your classical data into quantum computers. You can process them in a completely parallel way using this superposition principle, but what's going to happen is that at some point you need to make a measurement, right? And all of this parallelism is lost. So this does not mean that it's lost for good. It means that you need to write your algorithms in a way that can leverage it properly. Same with the measurement concept. So that means that you're basically building stochastic computing algorithms. Okay, there is some level of stochasticity that is intrinsic in the Born rule, in the way we measure a quantum state, and this is also something that needs to be leveraged properly when we decide in the way we decide to design our tasks. And there are more other things. Some of those are not necessarily relevant for quantum machine learning applications, but something that is important is the reproducibility of those algorithms, because this is it's a more general problem, and it's not entirely understood how this is something that we can apply at the moment on quantum computing. So when I talk about quantum machine learning, I will be talking about using quantum system to improve machine learning algorithms, whereby improve, I mean actually a lot of different concepts depending on the task. Please note that there is a very lively field also built of people that are actually using classical machine learning to improve quantum systems. For example, to characterize quantum errors or improve in general the design of systems of qubits. This is not what I will talk about. So I said improve. By improve, I mean what people typically think about when they are designing quantum algorithms. So the idea of complexity and accelerations and speed up, but also understanding what are the possibilities of building machine learning models which are able to represent more complex probability functions. At the end of the day, training a machine model is all about learning the probability distribution function that characterizes your data sets. Okay, then you can use that knowledge in many different ways, but that is the core of the task you're trying to do. And so the idea is that, or the question we're trying to understand is whether using a quantum implementation for a trainable algorithms, we are able to actually learn more complex PDFs. So this is what's written there as representational power, okay? What we've also seen is, for example, the fact that you can possibly train those models using much smaller data sets. Depending on the use case, this is something that can be useful or not. Typically in physics, we are not very much worried about that. We have the opposite problem. We have too many data and we need to, learn how to process that. But that can be interesting in some cases. And I have an example in the backup if you are interested in that. And then there is the whole discussion about energy efficiency. This is not specific to machine learning algorithm. It's particularly important for classical machine learning algorithms because of the size, the typical size that these new models are being trained today have reached, and because of the amount of computing resources that are needed to actually train them properly. So the question here is whether there will be some moment in the future in which maybe quantum computer will not give us necessarily speed up in training a model, but will be much more energy efficient. Okay, so it looks like a very far-fetched idea at the moment, given the state of the technology today. But I would like to point out that this is a concept that should be taken into account from the very early stage in the development of a hardware and in the development of algorithms and all the related software stack. Okay. So when people talk about quantum algorithms, and QML is part of those, this table is what you typically see. The idea of applying quantum algorithm to classical data or to quantum data. And so you can characterize then the different kind of performance improvement that you expect with respect to the type of the data you are looking at. And in the examples that you see, most of them that I will show you, most of them are related to applying QML to classical data. We also have an example of a simulated quantum data, and I hope I can get there at the end of my talk, but it's a very nice example, and let's say a demonstration of what the future applications could look like. And the last thing I wanted to, the last two things I wanted to stress are what's written at the bottom of the slides. We are a research lab. We are interested in solving problems that are related to our experiments or are useful for our theory departments or our engineering teams. So those are very applied kind of projects. We are interested in understanding whether this technology is something we can use in realistic applications. We are not necessarily interested in, in the kind of problems, for example, that were used. I don't know if you remember the announcements about quantum supremacies in 2019 that were published by Google. This made the news, it made a very big splash in the news, actually. That was, that was a demonstration of a very, very specific ad hoc problem that has very little to do with real life problems, okay, in different domains. So that is not what we want to do. And the last thing that's important is that quantum computers are actually already here. They are starting to be accessible through hybrid setups, and they are starting to be matched to classical computing infrastructure through HPC Center, through cloud providers. This is something that really allows us to do research, again, at a very practical level, but it's also kind of driving the kind of algorithms we are interested in developing, okay? So in most cases, what you will see are hybrid algorithms, in which part of the calculation is offloaded to the quantum processor. So within this context, in 2020, so now 3 years ago, CERN launched the Quantum Technology Initiative. The idea was really to go through the steps that I just mentioned to you. Understanding what are the practical applications of quantum computers for high energy physics. And we had had 4 main areas. And I'm talking to the past because the Quantum Technology Initiative, its first phase is ending now in December. So we are kind of drawing now the results of these first investigations. And I'm really happy to say that this has been reapproved, let's say, for a longer term, for a second phase. So we can continue doing this work. So the 4 areas of interest are listed here. I'm responsible for the quantum computing part. That's why I'm here. And if you want to know more about this, you can have a look at our roadmap, which is a public document. So let's go to quantum machine learning. This is the most important topic I wanted to discuss. So if you work on machine learning, or if you heard about it, probably you are very familiar with the typical machine learning life cycle. What does it mean to actually train or to build a machine learning algorithm? Those same concepts are also at the base of quantum machine learning, the way we do it today. So if you look at this cycle here, the ML life cycles, you see that there are different steps. Some are related to data preparation. So you need to typically analyze your data, understanding, extract the features that are relevant for, most relevant for the task at hand. Then you can use them for the training of your models. You need to choose an architecture, so there are different options. There are different ways of doing that. You do the training, which is basically an optimization loop in which you run typically a gradient-based algorithm that will try to find the minimum, assuming you have one minimum, which is almost never the case. Then you test your model and you basically iterate over this. Now, all of these steps are also what we do in a quantum implementation, okay? If we really were to look into the details, I could say, for example, that the data preparation is a big difference with respect to what you do classically. The tendency now for deep learning, for example, is to try to reduce the feature extraction to the feature engineering to the minimum, because you really want to leverage the full power of the deep learning model so that in an unbiased way. This is still not possible for quantum implementation. Actually, the way in which we select and we pre-process our data is very, very important. And also part of this step, if we're talking about classical data, is the way you load your classical data on a quantum system, okay? And this has a very strong impact on the performance of your algorithms. And I will show you something about this. Yeah. So what does it mean exactly? Well, I don't think I need to go into the details of this, but basically what I want to show you is that there are many different options. So as I said, we want to leverage the superposition principle to achieve at the maximum possible this exponential speed up that you expect by simply trying to use n qubits to load to store 2 to the n classical bits. Okay, you can do this, for example, if you use amplitude encoding. It's a standard procedure. Now the problem is, if you try to do this with current hardware, is that you end up with very deep circuits that are very difficult to run in a stable fashion. Okay, so what you end up doing when you need to decide what is the best possible classical data embedding on your quantum systems is trying to find a sort of compromise between, leveraging the theoretical advantage that you'd expect from using quantum systems with the performance that you actually get at the end. There is that point. What I also wanted to mention, those are 2 examples from 2 different papers. Those are classification problems, relatively simple. You have typically a signal versus a background, and you want to just classify whether the events belongs to one class or the other. Doesn't really matter now which one they are, but those curves are there to show you that if I use the exact same classifier and I change the data embedding, so the way I represent my classical data on the quantum states, I can have different performances. So this is something that cannot be forgotten. And if we talk about models, I think Stefano yesterday talked to you about variational algorithms that can be trained as examples of machine learning, of quantum machine learning algorithms. He talked to you about quantum GANs, I believe, but more in general about the hybrid loop, which you can build parameterized quantum circuits and you can adjust the parameters of those circuits or those gates using this classical optimization loop. So that is one of the ways you can build machine learning models, quantum machine learning models, and it's what's represented here to the right. There are other options too. A way of doing this that is very elegant is the concept of kernel methods. Those are well known also in classical machine learning. The idea is that the idea behind kernel methods. Are you familiar with those? In the context of the, okay. So if you have a problem, you have a certain data set, you want to understand specific features of your data set, what you can do is to try to find a mapping that transforms your data from the original space into a more, I would say, into a different space in which, for example, the data sets are, your data are more separated. If, for example, you need to solve a classification problem. Let's say what you want to do is to find a representation of your data set that simplifies your task, okay? So this sums up to defining what's called the kernel function. Now, if you think about the way classical data is loaded, is embedded in quantum circuits, this transformation can be interpreted directly as a kernel function. So basically, you take your data in your classical space, and you load it, you embed it into a quantum space. You are building a representation in the Hilbert space. This can be interpreted as a kernel. So basically, any kind of algorithm that runs on a quantum computer could be thought of as a kernel method, the same way you define support vector machines in classical machine learning, okay? So this is very elegant. This was something that was observed already quite a few years ago. I forgot the exact year, but in this time scale, it's probably 2017 or something like that, right? So 2018, something like that, by Maria Schultz in a group. And so you will see a few examples of this, and then another class or subclass of algorithms that I really like to stress this because I think it's a nice parallel between machine learning world and the quantum mechanics world is energy-based machine learning. Energy-based machine learning exists in the classical domain for a long time, and it's one of those physics-inspired approaches to optimization. You can do the exact same thing, obviously, in a quantum computer. Why? Because basically what you need, what you can do in this case is to represent as an Hamiltonian, so as an energy function, your machine learning algorithms. And therefore, the optimization problem just comes down to finding the ground state of your machine learning architectures, okay? Those are the energy-based. This is the basic concept about energy-based models. And there are, and the examples in the classical domain are, for example, Boltzmann machines. Okay, so this might be a little bit abstract, the next slides, but I just wanted to make a point that QML is a very interesting topic. I think there is great potential. There are a lot of challenges related to trying to do machine learning on quantum computers. And those challenges are related to this keywords you see highlighted there. Some of them are common to classical domain, others are quantum specific. So I will try to give you a glimpse of what it means to do to discuss those challenges. However, this is a very, I would say, broad field for which that is still developing. So we don't have answers for each one of those problems. I just want you to understand that it's not just about training a classifier and getting a nice ROC curve or getting a nice accuracy in your binary classification problems, okay? It might be that you do that and you get a nice result, but maybe you don't really know what's happening under the hood, okay? So just to say, this topic is something that is profound. That's what I wanted to say. Okay, so what are those keywords? Classical intractability is something that we all want to achieve. Okay, what is the point of building a quantum algorithms for machine learning if in any case, in any way, I'm using an algorithm that I could simulate classically? Then I'm better off running a cluster on a cluster of GPUs. Okay, so what we want to build are algorithms that for which I don't have a classical counterpart, or at the very least that exhibit features, for example, in terms of entanglement, that are useful for describing my data and that I cannot easily simulate classically. Okay, so this is the idea of quantum intractability for machine learning. Now, obviously, if you do that, not obviously, unfortunately, if you do that, you can end up into problems that are related to those other expressions that you see there. So expressivity, what is expressivity for a quantum algorithms? This is general, is how well I can survey the Hilbert space. How broad is my search space? Okay, so you want to make sure that you are able to find, to include in your search space the optimal minimum. The problem is that if your search space is too large, then you might just get lost into it. And so you increase your expressivity, but you end up with models that cannot be easily trained, okay? That's a very big issue. And the last point that I wanted to make, and I will give you a little bit more details about this in the next slides. The last point I wanted to make is generalization. Now, this is a problem, again, that we have in common with classical machine learning. It's a very big problem, and it is related to how much you can be sure that the algorithms you trained on a specific data set is actually applicable to to events that do not necessarily belong to the same probability distribution function. Okay, so this is a pretty interesting problem. It can be formulated in many different ways, and I repeat, we have it in common with classical and quantum, with the classical algorithms. So let me give you just an example of what I mean. So I talked about the problem of building models that are not easily tractable from a classical perspective. So let's take one step back. Let's start from the beginning. I have a certain set, I have a data set, and I want to classify signal to background, a signal from background. It's a binary classification problem. I want to do this with a quantum algorithm. Now, first thing I do, I have, for example, Higgs classification. I build the Higgs as a set of, I studied, I don't know, a specific decay, the two gammas. Okay, I have a set of features that describe my gammas. I need to find a way of representing those gammas into my quantum space. So I build a kernel function, and I want to build it in such a way that is not classically tractable. Otherwise, I can do it classically. Now, if I do that, as I said before, what I can do, what the problem that can arise is the fact that I have such a large training space that I'm not able to find the minimum anymore. Simply because the data sets that I have is spread out so much that when I run my optimizer, I cannot move from one to the other. What this translates to is a loss of predictive power, basically. I'm training my model, but it's absolutely suboptimal. It is not actually learning any distribution. It's not learning how to separate one class from the others. Now, this is something that has been actually observed with the easiest kind of kernel that you can think of, which is the fidelity kernel. It's just, I think it's written here. Yes, and it's just a projection of one state on top of the state that belongs to a training point to another, to a training point state. So this is my first problem. The second problem that I have is the fact it's related to the measurement and the stochasticity of my measurement. What can happen if I have this data that I have distributed over a large Hilbert space because I want to create a kernel that is not classically tractable, is that I'm going to have to need to do too many measurements in order to actually resolve my kernels. What's going to happen, and this is provable, I'm talking in a very basic level, but all of the references here will give you the exact, mathematical proofs of what I'm saying. what you find is that actually your kernel values, the vectors that identify the separation surface that I need to distinguish my signal from my background, will be so close to each other that I will not be able to actually calculate them. Okay, so this is a second problem that can arise. So one of the options in order to fix this is to play a trick, which is building specific kernels that I can prove that are actually still difficult to simulate, but are concentrated in a much smaller space in my Hilbert space. And there is this nice concept that was introduced by a few years ago. This was one of the first examples of quantum machine learning papers that were actually published on Nature. That proposes the idea of projected quantum kernel. Instead of building a kernel that is really describing the full surface instead of building a kernel that represents the full surface that describes your data set, you are working on the tangential planes. Okay, so you are working on a reduced representation of these data sets, and this can help a lot. You can actually prove, and it's something that the authors of the original paper had proved for general and toy examples, and that we have observed in a Higgs classification problem. You can actually prove that you get a much better accuracy in your classification if you restrict yourself into this smaller, I would say, into this subset of the Hilbert space. Maybe I don't spend a lot of time in talking about this. I just wanted to mention that I talked about trainability. There are also other problems that exist in classical machine learning and in general optimization problems optimization problems when those rely on gradient descent methodologies. And it's the fact that you can end up with optimization spaces that are really flat. And this is something that in the quantum case is a problem that becomes more and more important when you increase the number of qubits that you use to build your algorithm. So again, the connection between trainability, or let's say the tension between trainability and building non-simulatable quantum algorithms. There are many things that you can do. So this does not mean that you cannot actually train those algorithms. It just means you need to be smart. You can choose specific architectures that can help you ease this problem. You can use specific formulations of the optimization functions, the loss functions, and you can choose specific initialization points for your algorithms. Okay, so if you have a bias, if you have an idea where more or less your ideal configuration would be, you can try to start the search in a place that is close by. This is what I mean. So an example of this is some work that one of our PhD students has been doing on equivariant neural network. The idea here is that if you know about some symmetry in a data set, you can leverage that to build an architecture that conserves that symmetry, okay? And this is something we found that can be very, very beneficial for the training of those models. So again, introducing information we already have about our data sets. In this case, the problem looked at the images kind of data. And so the symmetries we were looking at were space symmetries, reflections, and rotations. This is something that can be generalized. And in fact, I'm looking for a use case, just so you know. I'm looking for a use case where I could test something like this for a physics case. Let's talk about it. What it's interesting, and this is just an example of I wanted you to see what I meant, and is the fact that the same architecture, if I implement it as a equivariant network, so as a network that's actually aware of this symmetry or not, I can have very different optimization functions. In particular, in this case, even if the symmetry is only approximately preserved, we can talk about how this is done in practice, but you see that even in that case, the loss function is much better behaved, let's say. Do you have questions until here? Up until here? I've lost you already. 6:30. Yes. Huh? No, these are digital computers. This is a universal. Yes. Not. This is quantum, but is semiconducting qubits that are built as digital computers for which, well, the universal computer. So we build a gate-based project. The parameters in this particular case, yes, the parameters on my networks are here. Sorry, I didn't explain this because I thought Stefano mentioned this yesterday, and I didn't want to. So the first block is the part that you use to embed your data. The second block is your, for example, classifier, is a network you want to train. So the parameters in there are all trainable parameters, and each one of the gates can be it's defined by one or more parameters that you train. And so those are quantum circuits. So there are many different ways that you can do that. It depends. Well, it depends on the architecture that the hardware technology that you're using, for example, because depending on the hardware you have access to or you are using, you will have different sets of native gates that exist, different sets of operations that you can run. Okay. In some cases, they can translate one into the other. For example, if you are talking about running on semiconductors versus ions, computers, okay, set of qubits. In other cases, it's completely different representation. You cannot map one into the others. For example, if you're using photonic-based systems, the kind of operations that you can run there, the gates that you can run there are completely different than the ones, and you parameterize them in a completely different way than what you do in the semiconductors. Was this a question? More or less. Okay. Okay. Are there other questions? Yes.
Okay. I just want.
Oh, yeah, sorry.
When you talked about reducing the dimension of the Hilbert space when you project the Hilbert space,
yes. What is it? Yes.
So if I understood this correctly, you basically reduce your dimension by using a smaller Hilbert space in the end?
You project it down. You have to imagine it, instead of optimizing your curve or your problem over a surface, you build a step of a sequence of planes that are at every given point are tangent to your curve. And that's where you run the optimization. So every time you are running, basically you are optimizing over a 2D space with respect to 3D, for example, if we were in the...
So aren't you losing information with respect to the initial...
You are, because in fact, this is the way you used to build your kernels, starting from the original, let's say the generic implementation.
So the final performance of the algorithm,
yes.
Is it good anyway, or what you lose with respect to the?
No, it's good. It's actually better. Again, I didn't really look into the, I didn't really talk about this. It's also the results are not so great. But basically, this plot. This is the system size. So how big is the dimensionality of my problem? The blue line is a standard kernel method, the easiest you can think of, that is implemented in a quantum circuit using the fidelity kernel. So just this projection kernel. You can see that this is the prediction error for my classification. So the blue line is actually at 50%. It means that my classifier gives me random answers. So the worst possible results I can get, right? So the red is the classical algorithm, which is much better. 40% is not great, but there is little optimization, it's much better. And you can see that as soon as I use a projected kernel, so the same problem, but restrict the definition of my kernels on these hyperplanes, you can think of them, suddenly I get much better prediction error. Again, not great with respect to many things we can do, but much better. Other questions? If not, I continue to, because generative models is slightly different. Okay, if I can continue. So generative models, what is the problem of generative models? Generative models are the coolest machine learning models you can think of. They've been possible, became possible thanks, I mean, in the classical domain, thanks to the explosion of data and computing power, actually. They're also at the base of all the most popular models you hear today, you hear of today. But in general, a generative model in its easiest formulation is just a tool that is learning, as I said before, the probability distribution function that describes a data set, and then it can be used to sample more events from this PDF. And the nice thing about it is that typically you don't need to know explicitly what is the form or the shape of your probability distribution function, but this is intrinsically learned by your network. And every time you run your network, you get events that belong to the same distributions. Now, so there are many different applications for this kind of models in physics. The first and foremost, I would say, is the problem of replacing Monte Carlo simulations, which are great, but are extremely slow. So you are probably aware of the fact that the community has been looking into classical deep learning for many years now in order to do that for those fast simulation approaches. You can also use those models to do many other interesting things. For example, to find anomalies, because if you find a description for the probability distribution functions that describes your data, and then you run your model over an event that does not belong to the same PDF, then what you'd expect to see is a red flag, basically a label or some metric that will tell you this event does not belong to the same standard model PDF. This is an anomaly. This is beyond the standard model, okay? So there are many interesting ways of using those generative models. The point that we wanted to make, but this is maybe a little bit too technical. I will just say it very, very fast, but it's not so important in the discussion today. What I wanted to show you with this slide is that those are very powerful models, but we need to be very careful in the way we train them. And in most cases, you can find also in the literature that many of those models are trained with suboptimal choices of their cost functions. Now, classically, you can maybe not worry about that too much because you run for 2 days instead of 1 on your cluster of GPUs, and you are going to get it anyway. In the classical domain, if you don't choose with some care your loss function, you might end up with untrainable models. And what we show here is actually the distinction. What we study in this work is really the distinction between using explicit versus implicit losses. So basically loss functions, cost functions that are already assuming some sort of shape for your PDF rather than not. Okay, so this is the bottom line. So the result of this work is that if you want to study, if you want to train a generative model on a quantum algorithm that does not assume any specific function for your PDF, then you need to use accordingly and what's called an implicit loss, like the maximum the maximum mean discrepancy loss, or the other way around. I never remember. Okay. And we actually, there is a whole study that's been done from a theory perspective on this, but we've also actually seen it happening in a real application. So the simulation of some HEP detector, high energy physics detector data. And the only reason why I'm keeping this slide here, because otherwise we run out of time, but it's just that this slide introduces a born machine, which is a very nice generative model. I think it's interesting because it's a generative model that does not have a classical counterpart, and that's why I wanted to show it to you here. I believe yesterday, Stefano talked to you about quantum GANs. Those are among the most popular models in classical domain, and therefore also in the quantum domain. I think born machines are nicer in the sense that they are very simple and elegant. Born machines are, the concept behind the born machine is really so you build a trainable state, so you build a parametric quantum state, you train the parameters so that your quantum states represent your PDF, basically. And therefore, every time you make a measurement, basically this measurement operation corresponds to sampling from your PDF, and you need nothing else. You need no original, external stochastic sources of any kind, and nothing. Okay, so everything is a pure consequence of a quantum domain. So you can use those kind of models for generating events, and this is some example that we have run already a couple of years ago. Where we had tested it as the Born machine, quantum Born machines, as solutions for building multivariate distributions. This was a specific muon force carrier model, a specific BSM models we got interested in because of the interests from our collaborators. But you could actually apply this to any kind of event generation problem in which you want to generate multiple features of a I don't know, in a final state. And what we found out are two main things. So if you look at these histograms here, you can see that up to a certain extent, and when your quantum systems is relatively small, we are not that much affected by error and all of these problems about decoherence that are well known for quantum computing. Of course, if you go beyond certain sizes, that's not so true anymore. But the nice thing about trainable systems, when you have data in them, so I'm not talking about variational quantum eigensolvers, if you do that, then those systems can learn actually how to compensate for noise. And you can see this because we have very nice agreement between the simulators and the hardware and the real and the expected performance. This is the energy of the outgoing muon, the generated energy. You can do this as a multivariate, so you can decide that you want to generate simultaneously multiple distributions. And that works very nicely too. Now, one thing that you should notice right away is that those distributions are binned, and I would say they're also relatively coarsely binned, so the resolution is not great. This is the main, today is the main, disadvantage or limitation of this methodology. We need to discretize our distributions if we want to run them or if we want to reproduce them with the basic implementations of Born machines. Okay, so not all problems, of course, are suitable for being approached this way. Okay, this is, I would say, it's an important thing that needs to be stressed. Actually, this exercise went further. There is the problem of building conditional probability distribution, which is very much a realistic problem. If I am using, if I want to simulate the energy distribution for a muon that has different initial parameters, I need to be able to input this to condition my generation probability using those variables. And so we also proved that we could do this with the quantum implementation. Anomaly detection, since I mentioned it, maybe I will just quickly show you this. Well, okay, I don't need to go into the introduction about new physics at the LHC. This is really not the time. We need to go eat. I can go one after the other. There's nothing here. What I wanted to say, though, is the fact that what we are talking about is a model agnostic search. Okay, because this is what's nice about those models is that you don't need to necessarily assume any specific model for training your classifiers. Okay, what you're going to do is to train your classifiers on standard model physics. And as I said before, anytime you get something that is beyond the standard model, your classifier will flag it. Okay, of course, then you need to understand what that is, but that's another problem. That's a problem for phenomenologists. So This use case is also showing you how we typically build in practice those models. And it applies to basically all of the examples that you see or read about around. As I said, those are all hybrid systems in which you have your data set. You typically need to run some sort of classical algorithm that can reduce the dimensionality of your data. In this specific problem, we are looking again at the Higgs to BB bar decay. And so we start with the order, okay, we start with order hundreds of features. We cannot today run or load easily hundreds of features on our quantum systems. So what we do is do some dimensionality reduction with the classical machine learning algorithms. And then it's that reduced data that we run through quantum classifiers. And those quantum classifiers are completely unsupervised in the machine learning jargon. So as I said, again, they are only trained on the standard model, or in this case, on background data. Those are the details of what the event looks like. So it doesn't really matter at the moment. Or maybe the only thing I can stress, which is interesting, is we are looking at the events that have at least 2 jets. And those jets are built using 100 particles each. And for each of the particles, we use 3 features: momentum, angular distance, and the third I forgot. Yeah, the 2 angular distance, and then phi and eta. So what we in total have 300 classical features, and we restrict them to 4, 8, and 16. So actually what the quantum computer sees is only 4, 8, or 16 variables that we have extracted out of this 300. Okay, so this is very big compression that we do. We build a kernel machine. We run it. I can explain to you the details if you're interested. We run it in this unsupervised fashion. There is a specific way you need to design your loss if you want to do that. But what's really nice is that if we do that, in spite of that strong dimensionality reduction that we need to do, is that, so this is tested on 3 different BSM models. There's 2 gravitons, I mean, and there is another boson, doesn't matter. Those are examples. In all cases, if we compare the quantum performance to the classical one, we get we get better performances with the quantum algorithms. They're not very much better if you look at the scales. Those are all log scales. Okay, so it could be something that is actually not so meaningful. But actually what we did was to go and look at what actually happens when you want to use this in a real application. When you want to use an anomaly detection tool or a classifier in a real application, you need to decide whether you are most interested in having a strong efficiency and maybe giving up a little bit on the fake rate that your algorithm is allowing through, or the other way around. So if you do that, and so you choose specific working point, then we start to see that the quantum algorithm actually does much better than the classical one. This plot shows you a ratio between the accuracy you get from, actually this was fake rate, so it's the other way around, doesn't matter. So you want this ratio between quantum to classical to be above 1. This is what you want. And the different points are different entanglement configuration that we use to build our circuits. And what you see is that this has actually a very big effect on the performance of the algorithms and on the amount of advantage we get with respect to the classical algorithms. Okay, this for us was one of the initial results that really showed that you can get very different performances thanks to quantum effects, not just the classical side, not just the optimization step, but really thanks to how much of the quantum, I would say, correlation, so of the entanglement, you are able to leverage, to use. Okay, I only have 2 minutes. I didn't manage to go into this part, but maybe I can go at the end of my talk. So this, otherwise it's, this is the PDF right there. Right. There are many, many examples here. I also wanted to show you something else before we close as a last example. 11, huh? 11, no. Can you still see? Do I need to go to? What's happening? Okay, can you see like this? I just wanted to give you a slightly different example of how you use those, how you can use this model in more complex problems. So here the problem is Monte Carlo integration. Again, I don't think I need to tell you how expensive that is, but how important it is, for example, for future multi-jets events simulations at the ILUMI LHC. Okay, so this is a big, big issue. You can use quantum computers to solve this problem, to do Monte Carlo integration using quantum amplitude estimation algorithms. If you want to do that, that's a very effective model. It leverages Grover's algorithms, and therefore it gives you a quadratic speed up. Now, the problem, though, in real application, this doesn't happen very often because the bottleneck is in the way you load your classical data or the function you want to integrate on your quantum systems. So are there alternatives or ways of speeding this step up so that you can actually leverage quantum Monte Carlo for doing Monte Carlo integration? So the answer is yes. You see here an example. This uses another one of those the quantum gun I mentioned before. Again, generative models. The quantum gun learns, is trained on the data that represents the function I want to integrate, learns this function effectively, and then it becomes the first step of my quantum amplitude estimate algorithm. This is an approach, and it worked very nicely. Here you see an example for a parabolic. Yes. Oh my God, how you say this in English? X square distribution. Okay, it's there. Another approach. This leverages a slightly more recent approach to, yes, thanks. A slightly more recent approach to quantum Monte Carlo, and it's based on Fourier series expansion. So this is a procedure that was proposed also like last year, 2022. The idea is that you take your function, instead of integrating it directly, you do a Fourier expansion, you save your coefficients, and then you are going to do the integration of each one of the trigonometric functions, which is much, much faster. Okay. Now, the original work, of course, assumes that you somehow can do this Fourier Fourier expansion efficiently, analytically, or in some other way. So what we did, this is a PhD student, he's still working with us, is to basically build a quantum neural network. You see the little box up there that does the Fourier expansion for us. In this way, the whole pipeline is actually quantum. You have your QNN that calculates the Fourier expansion coefficients. You have the quantum amplitude estimation-based method that will run the integration of each one of your trigonometric functions. So in your terms, in your Fourier terms, then you put everything together and you have your result. And this, of course, this was run on the exact same X square, the parabola example that I showed before, and the results are very nice. There is a whole lot of discussion that can be done about the size of the problem, how many qubits you need to actually achieve some accuracy, and so on and so forth. But now we don't have time. So let me just, we skip this. We'll go to the end. Okay, I don't want to be too, too enthusiastic about this, but I actually am very enthusiastic about this work in general, this topic. I think I'm not here to tell you that quantum machine learning is a tool for everything and anything. That's absolutely not true, but I think it's a tool that has a lot of potential. And so I think it's worth trying to understand at this stage, what are the topics that we can actually address with it? Because the original work that we've done in the past has already shown us that there is a quite a range of applications that could profit from this. And especially, I would say the biggest limitation for QML today is size, in the sense that there is always this intermediate step that we need to run in order to classical step in order to reduce the dimensionality of the problem, the input to the quantum algorithms. But this, if you think about it, this is a temporary problem that we have now because of current hardware. When we'll be able, for example, to fully leverage this exponential speed up, not a speed advantage that I expect in the data representation, because I don't need to worry about the size or the length, the depth of my circuit anymore, we will be a big step ahead. So I think it's among the algorithms and general approaches that we need to keep studying. Thank you. Thanks.
Thank you so much. Okay, questions?
I had a question about the anomaly detection part.
Yes. Tell me.
I was just curious how, I mean, you just said that it's not going to be a magic bullet for every single problem, but with this particular example here, how general do you think this is for similar kind of problems that we might use it for in HEP? So I think you showed Higgs to BB, right? Do you think it's a general thing that would hold if we were going to look for some particle going to some new physics particle that goes to 3 things or 4 things or something like that? Would it always be the case that you expect the quantum autoencoders to be better than the classical ones?
I think there are good opportunities, but it's not a given in the sense that this specific case. So there's 2 things to say. The first is what I'm saying, the second I'll say later. The first thing to say is that the more complex the classical algorithm, I think the best chances you have of doing better with the quantum one. And we saw that, so if you look, so these comparisons are done using support vector machines, both in the quantum implementation and the classical ones. Now, if you look around machine learning models a little bit, you will see that there are much more refined tools or architectures that you can use to do the same thing than support vector machines. However, for this use case, the state of the art that exists today, for example, in CMS, if you go and search for this analysis, you will see that you don't get an accuracy higher than 70% with graph neural network. And this is what we get here. So this tells me that the quantum circuit is a very simple circuit. This tells me that if I extrapolate, I am expecting this to work better, the more complex the problem is. Now, however, the catch is that if we continue to do, the catch is here, is in the fact that what you see here still uses this classical neural network as a preliminary step to extract the features that I need for the quantum classifier. So to be fair, I'm not really, okay, it's not, I shouldn't say that, but let's say, to be fair, there is some portion, some part of my performance that's due to how well I can do this. And so, you know, we can debate whether this is entirely due to quantum. Okay, I can tell you in this specific example, we did check that, you know, this is coming from the quantum algorithms, but that step is always going to be there. I want to get to a stage in which I don't need it anymore, and then we can talk. What? Okay, the kernel in particular here is it's a simple fidelity kernel. Yes, it's defined up there. There's nothing very fancy. What's different about this implementation is the loss function, because we train. So typically, you would train a support vector machine in maximizing the distance between the vectors, so that you can separate the 2 classes. What we do here, I don't write it. Okay. What we do here is we train the kernels to maximize the distance with respect to the origin, to the 0, because I train using 1 class only. Okay, so the kernel method is finding the best surface representation that separates my data from 0. This is what it does.
Okay, another question?
Okay. So both the encoder and the decoder are classical. So the kernel is quantum. Okay.
Yeah.
That's fine. No, but this is not my question. It's another one. No, I'm curious about this machine which exploit the Bohr machine.
Yes.
What it is exactly? Because I think that does not have any classical counterpart, no?
There isn't a classical counterpart, because what you do is you use the Born rule to define your probability function. Basically, so you can imagine X is your data, and theta is the parameters you optimize. So in a typical architecture, what you would do, for example, in a GAN or in another classical generative models, what you would do is that you would build your neural network. You would train so that you fix your theta parameters. And then you need some sort of, depending on the model, it's called in a different way, but let's say some sort of random input that you can input to your network, to the train network, and get out the p theta the x, sorry, the x, the new x, the sampled event that belongs to the probability that I learned. In this case, I don't need that, because once my quantum state learns p, then by simply measuring it, I'm sampling. I'm sampling out of the quantum states.
Cool.
Yeah, very cool.
I have one question on the ROC curve that you show for the anomaly detection. The fact that the classical approach performs worse than the quantum approach by some factor tells me that for whatever reason, the classical approach didn't quite learn the probability structure of your problem.
So yes, maybe we optimized the SVM. So we ran hyperparameters, but I did not go and see why this doesn't happen. So if you're looking for an explanation, why
that's what kind of I was hoping for.
So, but this connects to what I said before. Those are the classical one. Again, to be fair, those are support vector machines.
Alternatively, did you make the effort of using a classical approach without quantum computing at all?
Yes.
But you use a different architecture than support vector machines. That would kind of tell you by how much the classical is penalized by the fact that you can only compare the support vector machine in this plot.
I didn't do it myself because we have the official CMS results. CMS results, if you go look at the
are based on support vector machine.
They don't use support vector machine. They use graph neural network. I don't have the reference.
Okay,
and this is what I meant before, that you get an accuracy that is around 70%. So it compares to this.
It's comparable to the quantum support vector machine implementation. No?
Yes, it's in the same scale of both of them. I consider them very similar. So
okay. Thank you.
But this is a more general point.
So it's a related question, just to make sure I understand. That what the quantum device is doing is it's mapping the space of R, L-dimensional R, onto a classifier. And so it ought to be that there's some classical function that one can write down that does that job equally well if one can find it, I think. Isn't that right?
Yes. So this connects to the discussion I made at the beginning about writing a quantum algorithm in a way that I cannot do classically. Because at the end of, if I were to actually use the full power of my Hilbert space, so define my kernel over the full space, I couldn't represent that classically in an efficient way.
So in this case, is it possible to write down such a function? I mean, in principle, is such a function, is it representable as a function?
In principle, you could.
Yes.
It's just that I cannot do it today, otherwise I cannot train it.
Yeah, okay. So that makes it a sort of, you could export it back and potentially find so you can maybe do the training quantum and then use a classical algorithm to do the classification in the end. Is that right? I'm
not sure what you mean. So you're talking about two-step thing? Because wait, maybe the thing is that, so the classifier is the quantum algorithm. So it depends if you're talking about comparing a purely classical classifier to a quantum classifier, or whether you are combining the two.
I'm trying to work out if the advantage is coming in the training or in the classification, I think.
I'm training the classifier to do the classification.
Yeah, I know. Yeah, okay.
I'm sorry.
Let's chat.
No, but let's chat because I didn't really understand what you mean. So, okay, let's talk. Okay. Yes.
So I just noticed that you have some spin example that you skipped. Can you just say a few words on that?
Spin example that I skipped. So I had a spin example that this one.
Exactly.
Oh, sorry. Well, this is a different. So this is a classification problem. The interesting thing about this is that so we build a quantum algorithm that simulates that Hamiltonian. So calculates the ground state of that Hamiltonian, and then what we do, we vary the parameters in the Hamiltonian, so we obtain states that belong to the different phases.
Right.
And then we classify them. So then we train a quantum algorithm to do the classification. This is what we do here.
Oh, I see.
So the first part of the algorithm, the blue box, is a variational quantum eigensolver algorithm. Is an algorithm that you can use to calculate the ground state of the Hamiltonian, the any Hamiltonian I showed up. So we do that. We don't measure the state, so we keep the quantumness. We keep the
You just keep the ground state superposition, right?
Yes,
Yeah.
we keep it there. We generate many different one of them for the different that belongs to the different phases, and then we train this network to classify it correctly. What happens is that you can reproduce almost perfectly the phase space diagrams. That is, those are the output of the trained algorithm, so of the machine learning algorithms. And so there's two details here. One is the fact that this is an example of running QML on quantum data, because the input is actually the output of that algorithm. So it's my quantum state, I don't measure it.
Right.
So this is the first thing. Second thing is that if you notice, there are those red dots there. Those red dots in the phase diagrams are the points I can calculate analytically, in principle, for which I have the analytical solution. And those are the only points that we use for training. But those are enough for the network to learn the full diagram. Okay.
So that's quite strange, because from the boundary, you know the middle part. So that reminds me in scattering theory, you have mapping input into the output. You need a very smart, boundary thing.
Okay, but the thing, so okay, let me be how can I say candid here. So we first time I saw this, I was very happy. This is a proof of generalization. I can train my model on the boundary PDF. How you call that? Do I write it? I forgot the name. No, okay. So I train my model only on specific points. Yep. Yes, I forgot. There is a specific name I forgot. Sorry, but the network learns how to extend. So from the distributions that it learns. So out of distribution generalization it's like the holy grail in machine learning. But actually, this is not a very complex model. The ANI model, what happens is that the points, the red points that are in the blue area and the red points that are in the yellow and the ones that are in the green, they represent very well those three classes. So the network learns. And in fact, it learns the boundaries also very well. But this diagram can actually have, if you increase the order, can have higher order transition. There is a line, a floating phase transition that happens, and it's almost horizontal from K, going up from K equal 0.5. And the network doesn't see it at all. As you can see.
So what is the size of the physical system that you used?
So this, I didn't write it. So we did two tests. Yes, it's written there. It's 12 spins.
12 spins. Yes. So it is on IBM computer, right?
Yes, this was run on IBM.
And the biggest one that you used was what? How many qubits?
For this problem?
In general.
Oh, we just recently ran with 64 qubits.
Oh, I see. Okay, so still there is some space.
Problem.
Yeah, of course. But still there is twice as much.
It's a lot. Basically, it's the evolution, I would say. You remember one of the first slides was the equivariant neural network?
Mm-hmm.
This problem we run with 64 spins. This is actually another, sorry, I thought this was, I told you this was an image classification problem. We applied to the MNIST. This is some images that machine learning people use to train their model in classification. But then we also created images out of an Ising model, and we ran it. Right. We ran the classification there, and it actually works.
So finally, just to grasp the point, there is this trade-off you told at the beginning. So if you have a very big Hilbert space.
Yes.
And you have a lot of states, then sometimes you cannot retrieve the information back. This is also in standard quantum algorithms, That's why, you have this, how they call it, this PAPs and so on.
Yes.
So my question is, what is here? I mean, I'm asking about the intuition because there is no convergent proofs here, right? Convergence proofs. What is the intuition that you have a big Hilbert space, you make a lot of superposition, but then you somehow retrieve the information that is important, because you have the Barren plateaus and all the other stuff that are there, So that's what's the key point there?
So I think the key point, for me, there isn't one key point. There's a few of them. The point is that they are so related to you need to use as much of the information you have on your data in order to design the answer, because this will shape the optimization space, design the loss function. The more local it is, if you can split up your loss function, so your big problem into sub problems, so you build local functions, then you are less affected by all this, I would say, high dimensionality in your search space. And you need to try and use noise in a smart way.
But this is really something more than Grover algorithm, because you somehow boost totally. At the first glance, one would say, okay, as you said, I have a little bit of feature, and I boost it up, okay?
Yes.
But we know that the standard Grover speed up, it cannot be more than quadratic.
Yes.
So the question is, do you believe that here you get more than quadratic?
So the thing is that it's a different kind of, so the quadratic speed up is something we can apply to the single step. But then I need to multiply for the number of steps that I need in order to actually solve them.
Right.
So in that sense, I can do better than in a classical, because if I need fewer steps, then I build a better algorithm, and each one of the steps can be faster. So that is that. However, there is the discussion about the kernel's concentration, or there is a similar thing that is valid for variational algorithms. So it's really more general than kernels. But here, there is also the discussion about about the statistical uncertainty that is associated to my measurement.
Sure. Mm-hmm.
So from practical point of view, the number of times I need to run a circuit today in order to have a reasonable measurement has a big implication on how efficiently I can do this. And if I need to do 10,000 steps per circuit in order 10,000 shots, 10,000 repetitions, it's
yes, because exactly this point reminds me quantum metrology problems. When you have, you ask about whether you can separate maxima. It's in quantum optics.
It's the same problem.
So basically, you should have some. But let's discuss it later, I think.
Yes,
right. Thank you very much.
Those have mathematical proofs in there. Okay, so this is not just observation.
Okay, I think we need to close here.
Yes,
Okay,
let's go eat. Sorry.
You can discuss with her. Are you around tomorrow for dinner?
Yes.
Perfect. You can dinner. Thank you so much again.
Thank you.